Hi, and welcome back to Leslie's Lab. In this episode we're going to take a Raspberry Pi camera and strip the Bayer filter off it. This is probably one of the most extreme Pi cam modifications you're ever likely to see, so let's stick this on the bench and take a look. So this is a Raspberry Pi camera. This is what we're going to remove the Bayer filter from today. In case you're unfamiliar with what a Bayer filter is, let's switch over to the computer and take a look. So on the screen here we've got a couple of diagrams courtesy of Wikipedia. These are sort of cross sections of a CCD sensor, a camera sensor, right? We've got the silicon photodiode array here itself, so this is like a cross section of a single photodiode. So we've got our photodiodes here, we've got the metal wiring underneath that connects all of these together, you know, into rows and columns, but on top we've got this filter. So we've got a little color filter here where we've got blue, red and green, which are our subpixels for every one of our pixels, right? So we can detect individually the blue image, the red image and the green image. On top of that we've got a little tiny micro lens which helps to focus light into the individual photodiodes themselves. If we take a look at the Raspberry Pi's website itself, you know, all about the Pi camera itself, we can see what the Bayer array looks like. We've got a blue pixel, a red pixel, two green pixels, and this, you know, block of 4 up the top here represents an individual pixel of data. Now, why is it we would want to remove this? We'd want to remove this because this blocks quite a significant portion of ultraviolet light, and it also blocks quite a significant portion of infrared light, and it would be kind of nice if we could make a Pi camera see quite a ways into the ultraviolet, and it would be kind of nice if we could make it see quite a ways into the infrared. For my purposes, for previous videos, you'll have seen I built a Raspberry Pi spectroscope, and the spectrum of daylight isn't really quite what we'd expect it to be if we had like an even response across all of the pixels. If we take a look on the next tab here, somebody's kind of put up on GitHub the spectral response of the Omnivision OV5647 CCD sensor, and so we can see what we're looking at here. So there's our blue response curve, there's our green response curve, and there's our red response curve, and we can see that they tail off as you get into the ultraviolet. You know, you could sort of extrapolate this line down and it sort of disappears at about 370 odd nanometers or so, and this, the sort of red tails off. Now the reason for this is when we build cameras we try and duplicate the way the human eye sees things. So we're essentially trying to duplicate the general spectral response that you'd expect out of the human eye. We're not really looking at sort of scientific applications with regular color cameras, right? In fact, we can see this in the Bayer diagram for the Pi. We've actually got 2 green subpixels for every pixel that we're looking at because the human eye is very, very sensitive to green. What I'd like to be able to do is to strip that Bayer layer off and get a curve out of the camera that looks a little bit more like this, where we've got sort of almost a bell curve. Again, if we extrapolate down into ultraviolet, maybe we're down to maybe 200 nanometers or so on the left here. We've got, if we imagine it starts down here, we've got a nice bell curve of spectral response way up into the infrared as well. This has actually been done before. In fact, there's a couple of ways that we can actually attack the Bayer layer itself. You can actually physically scratch it off. This is something that's been quite common with like large area CCDs, like the big Canon sensors that you get in DSLRs. A bunch of people have been busy scraping away at the Bayer layer. It'll actually come off if you poke at it with a sharp stick or a needle. It's a bit of a rough way of doing things, and we'll get into why you can't do that with a Raspberry Pi camera in just a minute. But sure. I've got an academic paper here. A bunch of people down in the University of Sheffield took it upon themselves to get a Raspberry Pi camera, and they stripped the Bayer filter off so that they could image right into the ultraviolet with it. They used chemicals to do this. Specifically, they used DuPont EKC 830, which is a positive photoresist remover that'll, basically you put this stuff in a boiling solvent and it will remove it. There's other solvents as well that will remove the Bayer filter, such as Piranha, which is a mixture of sulfuric acid and hydrogen peroxide, particularly nasty stuff. I did try and get hold of EKC 830, but it's nigh on impossible as a private individual to be able to do that. I did get in contact with the company and they said, oh yeah, we can supply it, but you've got to buy 3 gallons of the stuff. And then that's a problem for me because I've got to be able to, well, first off, it's going to be hellish expensive, right? But I've also got to be able to get rid of the stuff as well. It's not like you can pour this stuff down the drain. It's really quite toxic, a toxic chemical. But yeah, so they had, if we scooch through the paper and see what the results results had. They put a little quartz lens on the front afterwards, a little filter as well, so that it could specifically pick out about 310 nanometers with a 10 nanometer full width half maximum, which means that you're looking at somewhere between like 305 and 315 nanometers, so well into the ultraviolet. And if we scooch down the bottom of the paper, we should see a little money shot. Scoot, scoot, scoot. Yeah, so what these people were interested in, they were interested in detecting sulfur dioxide emissions from chimney stacks. The way this works is the whole planet's bathed in ultraviolet light. You point your camera at a smokestack and you can infer the amount of specific chemicals in the stack absorbing the ultraviolet light as it passes through. So they've obviously picked like 310 nanometers because sulfur dioxide is like opaque at that particular wavelength. So you can actually do some cool stuff. You can actually image sulfur dioxide gas coming out of a smokestack, which is pretty cool. Yeah, fine. Let's switch back to the Picam here. Obviously we need to be able to get at our sensor, so I'm going to pull the cable out real quick and we'll take a look. Now the sensor itself actually disconnects from the PCB, and if we very, very carefully get a scalpel, we should be able to get it in between the plastic and the PCB and pop it off. Now it's quite a delicate operation. I've got to be real careful because we don't want to touch it. Awesome. So that's the lens removed. Whoops, let me go and get it. There's our lens. We can actually see the IR cut filter in the back of the lens there as well. So we'll just discard that. What I'm really interested in is looking at this dye under the microscope. So that's the sensor reseated. We can see the sort of rainbow pattern given off by the light. Awesome. Let's get this under the microscope and see what we're looking at here. So I've got the sensor under the microscope, and I've actually got a Raspberry Pi camera pointing down the eyepiece of the microscope so we can see what's going on. And I'm going to try and point with a needle under here at the various parts. So yes, so my needle's out of focus, but of course it is. Down at the bottom we've got our tiny little gold bond wires that we're going to be very careful not to touch. And in the middle we can quite clearly see our CCD area. Now if you look very carefully at the edges of the CCD, you'll notice the structure changes ever so slightly. So down at the bottom here, we'll see if we can point about there. Down at the bottom there's 3 rectangular blocks. Now these are either amplifiers or roll drivers or something, and in fact there's a border all the way around the edge of the CCD itself. Now originally when I wanted to strip the Bayer layer off this, I'd read that people have been poking at these things with sharp sticks, and I figured, well, we'll just put it under the microscope and we'll scrape that layer off. And right enough, you can actually get the Bayer layer removed off of the Raspberry Pi camera. The problem is when I was doing this, I started in the center. So I started in the center here and I was just sort of scraping away, scraped the Bayer layer off. I scraped off maybe, I don't know, a square millimeter or so, and then reconnected it to the Raspberry Pi, and lo and behold, Bayer filters removed, right? And it looked all very, very successful. The problem is once you get to the edges, once you get to down near these structures down at the bottom here, which are, like I say, probably roll drivers or column drivers or whatever, the moment you get down there, the moment you touch them, it actually destroys the camera. In fact, if you go anywhere near the edge of the image sensor area at all, it immediately destroys the camera. You suddenly get like vertical lines or horizontal lines, or it just goes off, and that's the end of it. And it turns out that at the edge of the sensor, as I've already said, there's either row or column drivers or amplifiers, but it turns out that although the sensor itself is back illuminated, which is to say that we've got like silicon before we've got interconnects, around the edges the actual opposite is true, and we've got our interconnects across the top, which makes things very, very difficult. So I destroyed plenty of cameras trying to work out why it was that cameras were dying, and I also destroyed plenty of cameras trying to chemically strip this stuff as well. Which is rather unfortunate. I have a box of dead Raspberry Pi cameras that I've been trying all sorts to strip this stuff off with. So as we've seen so far, removing the photoresist layer, the Bayer layer from a CCD camera is a delicate process, and the stuff that we're trying to remove is exceptionally tough stuff as well. It's really difficult to get rid of. I tried a whole range of solvents. I boiled it in DMSO. I tried brake fluid and all sorts of other bits and pieces that I had about. I bought some like industrial strength paint stripper off the internet to try and get shut of this stuff, and it just won't budge. So the last thing that we'll look at here is Excimer laser photoresist stripping. If you want to get rid of something that you sort of come across in electronics or physics or whatever, it's always useful to look at, well, how is it being done in industry? Industrially, they use Excimer lasers for stripping photoresists. I don't think it's ever been done with a CCD camera before, but it's certainly been done in the manufacture of silicon wafers. So if we have a quick look, if we read the abstract, it says a new method for stripping the most challenging photoresists on deep submicron technology semiconductor wafers has been developed using Excimer laser ablation. I do like to see the word ablation in there. So it sort of goes into a bit of detail about the sort of pros and cons of all these things. So it says, two main photoresist stripping methods are currently in use. This is back in 2016. There's dry stripping, which uses plasma. So basically, you direct a jet of ionized oxygen atoms at your workpiece, and it will strip. Oxygen's really reactive species, and as a plasma, even more so, and it'll strip off your photoresist. And this is actually quite common. And then we've got wet stripping, which uses acids or solvents or whatever, as we saw with EKC 830, it actually mentions piranha in the document. Piranha's particularly nasty. So they go into their little thing about the laser stripping process. So if we scooch down a bit, we'll find it. So the laser stripping technology, got a little block diagram down the bottom, whatever. They were using an Excimer. What I was interested in was, well, what laser are they using for this? And, is it possible to repeat this at home? So they've got a krypton fluoride Excimer laser at 248 nanometers. Don't own one of those, but I do own other lasers. So they introduce it into the process chamber via a quartz window and basically strip the stuff off. They use various gases fed into the process chamber as well to get rid of the organic molecules that are left over. But the paper itself, pretty useful, right? We can get some useful information out of this. Awesome. So it says about the ablation process and reactive chemistry and so on and so forth. It says each laser pulse that they're using there delivers a peak power of 16 megawatts. I'm under the impression that this is probably like 16 megawatts per square centimeter. 16 megawatts sounds like a huge number, but if you're looking at a very, very tiny laser spot on the surface of a semiconductor, you're probably, you're talking like millijoules maybe, right? When you read papers like this, you've sort of got to think about what it is that you're looking at. So you're using a high peak power laser to effectively disassemble the layer, or ablate the layer as it was. As I've said before, this layer is organic, and all organic molecules will degrade under ultraviolet light. It's just a question of how much light you can actually couple in there. And there's nice little diagrams, they're using processed gases to get rid of organic molecules and so on. I don't own a krypton fluoride Excimer laser. Those things are incredibly expensive and contain toxic gases. I don't really want fluorine in my house either. But if you've seen my previous videos, I actually own a fiber-coupled MNL100 nitrogen laser, which delivers, kilowatts per pulse. So I thought, well, I wonder if we could actually strip the photoresist layer off with one of those. So this is my solution for stripping the Bayer layer off of a Raspberry Pi camera. This is definitely a YouTube first and possibly a world first, although people have used lasers to strip off photoresist before. As to my knowledge, I don't know of anybody that's ever used one to strip off the Bayer layer off of a camera. So let's have a look at this this setup real quick. We've got an XYZ stage that I picked up off eBay, and these are all driven with little micrometer heads, which is fantastic, right? So if we want to change the focus, we can alter our Z-axis, and we've got our X and Y axes here. What I've done with these is I've mounted pulleys on the end of them that I'm driving with a pair of stepper motors. This is a job that you can't reasonably do by hand. I did try it initially, where you just sort of cycle the thing left and right and up and down until you sort of strip the layer off, and it takes a very, very long time. It's very, very inaccurate, and accuracy is key with this. At the back we've got a Raspberry Pi that's just sort of tucked down there out of sight, that just has two DRV stepper motor drivers on it, and I've written a small program that goes through the whole routine. But that's not where the sort of heart of the thing is. At the top we've got a USB camera so that we can see what's going on, and also point the beam where we want it to go. And then on the left here I've got a fiber optic feed from my MNL 100 nitrogen laser that I tore down in a previous video. Now this produces several kilowatts of peak power in the ultraviolet, 337.1 nanometers, and that should easily be absorbed by the Bayer layer and the micro lenses to the point where we can actually essentially blow them off there. So this is connected up to my fiber launcher that I used in my dye laser project, and then that's finally focused with an objective lens at the front there. It's actually, you know, a reasonably straightforward setup. Let's turn our attention to the computer and see what the computer sees. So we can see our window here. We can see all of our bond wires at the side of the CCD. Incidentally, the coating itself stretches right the way across the silicon. It covers the entire surface of the die. We can see it's got a sort of curved edge down the bottom there, and the silicon die itself is obviously square. We can see some structure in there as well. There's a little bit of structure inferred under the blue. And then we've got our main image sensor area in the middle. We can make out our row and column drivers, so they're all the way along the edges there. And you know, they're either row and column drivers or amplifiers. Whatever they are, we can't touch them, right? So we can't poke at them with a stick and expect everything will be just fine. There's a little square on there. It's a square that I've put there deliberately on purpose. This shows us where the beam is focused. So if I just jog sideways a little, if I put the nitrogen laser on burst mode, we should see it evaporate some of that photoresist. So there's our photoresist evaporated. It looks like the calibration is a little bit out, so we'll just alter that square. Awesome. Yeah. So the thing to do now is to line up with our image sensor. Now we'll start at the corner there because we want to edge-to-edge strip. So when this thing pecks away at the surface, although the spot is something like 100 microns in diameter, so if you imagine like this whole length here is like 6 millimeters, the sort of center of the spot is about 100 microns or thereabouts, but we're actually going to strip away like a few microns at a time. So we're going to strip from left to right, and then we're going to move down one, and then right to left, and then move down one, like raster, like a television raster. Now this process is going to take a very, very long time. It's going to take about half an hour. Obviously nobody wants to sit watching this for half an hour, so we'll probably speed this portion of the video up. But let's fire up the laser. Well, better fire up the stepper motors first. Just check that they're engaged. Awesome. So I've got power to the stepper motors. We'll just fire up the laser. So we'll just set it on endless repetition. Now we'll begin the strip. So we can see that we're removing photoresist as we go along. It's scattering it all over the place. We don't have to worry too much about that. We'll maybe occasionally blow that off there. So we can see it nibbling away at the edges of the photoresist, nice as you like. So we're just over halfway through the strip now, and we can see the bottom half of the CCD is, you know, obviously unaffected. It's still got the Bayer layer on, and if we watch closely we can see the nitrogen laser chipping away at the edges of the Bayer filter there. You'll have seen me maybe, because we've been speeding this video up, but maybe you'll have seen me come in occasionally with a large syringe. This is just to blow away all the ejector from the surface. I'm sure, you know, if I was to refine this somewhat, you know, if I was to maybe do this on an industrial scale, we maybe would have process gases removing all of that stuff. But so far so good. Everything's looking really, really nice. So now that the stripping's complete, we can have a look at our work. So we'll just manually jog back through, and we can see that we've successfully removed the entire Bayer layer, as well as the lenses. They're all away. And we've managed to do a nice edge-to-edge strip as well. Excellent. There's a lot of dust and detritus all over my CCD sensor. We can get rid of those. We'll just give this thing a wash with isopropyl alcohol. But yeah, excellent. You'll notice, you know, I said before that, you know, if we damage the row and column drivers, we can actually do harm to the CCD, but the laser just doesn't touch them. I mean, they're not fussed about having the photoresist stripped off them. So excellent. You'll notice as well, there's some lines on the surface of the CCD. Those will sort of diminish with cleaning anyway. You'll notice it's quite interesting when you do this. Down at the bottom here, there's these two very dark lines, and I've noticed these before, and originally I thought that perhaps I'd stripped too hard and taken away the anti-reflection layer, but it's just refraction of light through the CCD surface, so it's perfectly fine. To do our final clean, just to get rid of the dust, I've got some IPA in a beaker, and we'll just give it a very vigorous blast with the syringe. This will dry off very, very rapidly. So before I can hook this thing up to the Raspberry Pi, I've just super glued on a little plastic M12 mount so that I can mount a lens on it. So let's connect it up to the Raspberry Pi and see what we can see. So I have the debayered Picamera hooked up to the Raspberry Pi here. We're looking at the output image in the center frame, and if I pick it up and point it around the place, we can see that we've got a wonderful black and white image, because of course all the color data is now missing. There's the oscilloscope screen. Awesome. As there's no infrared filter in this as well, we can see right through the red filters on the front of my test gear there. So there's a Fluke 8000 bench multimeter, and we can see the LED displays right in there, and ordinarily it just looks like dark red. Excellent. So far so good. There's a couple of little artifacts on the screen here. We'll just expand this. We'll be able to see those. The frame rate will drop obviously because we're using OpenCV for this, but yeah, in fact I'll just point it at the ceiling and we can see those. So we've got a reasonable white background. Yeah, there's a couple of little marks on the screen. These are either specks of dust or little bits of the Bayer material that haven't been removed. Perhaps it would be a good idea to have a second pass with the laser at this, just to get rid of those. I suppose the thing to do just now would be to see how this performs spectroscopically. So let's attach the Raspberry Pi camera to the spectroscope and run the spectrometer software. So I've set up the spectrometer and I've just done a quick calibration, and we can see the output looking out the window. A couple of interesting things to note. This is an overcast day here at the moment, and there are far more Fraunhofer lines actually visible as a black and white view than there ever were when we had a colour pie camera. So yeah, that's a good point straight off the bat. Secondly, compare these two spectra. So on the right, this is a previous image from the colour version of the camera, and we can see there's an odd peak at 582 nanometers. I've always thought this was very, very peculiar. In fact, it even shows up if you point the spectrometer at tungsten bulb. So it most assuredly shouldn't be there, and it is an artifact of the Bayer filter itself. As we can see with the black and white debayered camera, this peak is now entirely absent, so good. We've got the curve that we were expecting. If you recall at the beginning of the video when we were talking about curves, we were hoping that we'd have you know, essentially a bell curve that would start down in the ultraviolet and off into the infrared. We can see the Fraunhofer absorption lines all the way through the graph as well. They're really quite prominent now. Excellent. Yeah, altogether I'm pretty pleased with the results here. I suppose at this stage the thing to do, I'm going to tilt the camera left and right inside of the spectrometer housing so that we can see, well, how far into the infrared do we think we might be able to get, and how far into the UV do we think we might be able to get. So let's do that just now. So I've angled the pie camera in the housing and recalibrated it, so now we've got a point over here that's at 561 nanometers and a point in the middle that's 660 nanometers. So I've just calibrated these with a couple of lasers, and we can see some very, very dark lines off towards the very, very red end of the spectrum, and at this end we're approaching like 850 nanometers so far, which is not too bad. I suppose at this stage perhaps I ought to think about like rolling my own spectroscope so that I can get a very, very wide view of the spectrum, or perhaps we could try a new lens later on. Excellent. Let's see how far into the UV we can look. So I've tilted the camera the other way. I wasn't expecting to see terribly much in the way of ultraviolet because we're still using glass lenses and the spectroscope contains glass and plastic as well. However, we are seeing quite a little ways into the ultraviolet, so we're going quite past 400 nanometers, maybe as deep as 350 perhaps, at a guess. So yeah, not terribly too bad. The real thing to do would be to start using quartz optics with this to really get down into the ultraviolet. So although I don't have a real ultraviolet bandpass filter, I did pick up a filter off eBay that would pass both ultraviolet and infrared. I suppose the thing to do if we want to be able to see just in the ultraviolet is to cut out all the light in the room, so nothing is emitting infrared, and instead I've got a fluorescent tube here that emits only ultraviolet light. It's a black light, and we can see it quite clearly on the camera there. So we've excluded all infrared. If I take a couple of the cuvettes that I've been using for my dye lasers, these are strongly absorbing in the ultraviolet. This is actually glowing a brilliant green to my eye, but it looks quite black on camera because it's absorbing all of the incident ultraviolet light. So we are seeing UV on a pie camera. There's another cuvette as well. This fluoresces a brilliant blue and it looks really quite black on camera. Excellent. Since this lamp is relatively eye safe, I've got the lamp illuminating my face and the view is really quite interesting. I look quite dirty. I'm sure I'm not, it's just that the ultraviolet light is being absorbed by the skin essentially. It's quite an interesting view. You'll have probably seen pictures like this on the internet before, but yeah, very cool nonetheless. There's the back of my hand in UV. Looks kind of oily, right? All in all, the picture quality is not terrible. As I've said, there's a couple of artifacts left over from the process there. If I expand the image out, we'll just take a quick look at those. There's obviously a speck of dust or grot or something on there. And I did notice at very low light levels, there were striations across the field of view from left to right, which is probably little bits of organic material that's still left on the CCD surface. But as a home attempt, it has to be said, it's not half bad attempt at stripping the Bayer filter off at all. I've got a camera that's a little bit more useful for the things I'm interested in. Excellent. Thanks for watching this episode of Les's Lab. If you want to see more content like this, don't forget to hit like and subscribe down below, and I'll see you guys next time.